So welcome everyone. In this class, we are going to discuss about the thermodynamics. Thermo means heat and dynamics means movement of particles or energy. Heat or internal energy of a system is a function of temperature, where temperature is the measure of average kinetic energy of the molecule. So when we are measuring the temperature of a system, we are just measuring the average kinetic energy of the molecule. So we cannot say total kinetic energy of the molecule because uh, each molecule may not have the same amount of kinetic energy. So that is why we are measuring the average kinetic energy here. Because when we see, you can see from the Maxwell-Boltzmann distribution. So Maxwell-Boltzmann distribution provides a graphical representation of molecular velocities with respect to temperature. So you can see the distribution of particles among the velocities is varying from lowest value to the highest. Here, the most probable velocity is around here only. So not every molecule will have the same velocity. So we have to average out the our result around the most probable velocity. So in this range, the temperature of the molecule will be the average kinetic energy of the molecule. So we cannot take from here or here. So it will provide the wrong answer. So we are going to consider only the most probable outcome of the result from the most from the Maxwell-Boltzmann distribution. So Maxwell-Boltzmann distribution is a proof that not all molecule in a system have same energies. So molecules arrange themselves into a particular range of energies called microstates. So these microstates are the reason for the macroscopic behavior of the system. So that's how our temperature is getting. So because of the microstates, we are averaging out the temperature as a average kinetic energy. So that is how temperature is measured. So let's move on to the heat transfer. How can heat energy transfer between systems or between system and surrounding? So there are three mode of transmissions. First one is convection. Convection due to the movement of particles. Actually, just molecules. So here heat energy is transferred by the movement of molecules into the system or from the system to surroundings. So from the hot region to cold region, these particles are moving from hot region to cold region. That's how they impart kinetic energy into the cold system. So here in the hot region, the molecules will be vibrating at a higher rate. When they come in contact with the cold state, there they collide with the molecules in the cold state. So thereby imparting kinetic energy into the system results in the increase in temperature. So this is how convection transfers heat. So next, by conduction. So in conduction, what happens? Movement of electrons. Movement of electrons transfers heat from hot region to cold region. So here electrons acts as a conducting medium. So from the hot region to a cold region, electron is moving. This electron carries the thermal energy from one end to another end. Let's say, for example, let's take a conducting material like a iron rod. Iron rod. What is the symbol of iron? Fe. So let's take iron rod. If you heat it in the end A, eventually when the thermal energy is exceeding, then the end B, the electron transfers from this end to this end. So it's like a flowing current. So this heat energy converts into an electron current. This electron current transfers the thermal energy from end A to end B. Here the hot end is A, cold end is B. Until they reach the thermal equilibrium, they will start continuously transfer the heat from A end to B end. So for convection, we can say like transfer of heat in the atmosphere. So let's say land, heat exchange between land and ocean. So for example, when southwest monsoon is coming, wind comes from Arabian Sea to the delta plateau region of the South Indian region, where it causes rain. So here cold air flows from the ocean to the land, or we can say that hot air from land flows into the Bay of Bengal. So when air flows from one region to another region, there as a vacuum created. So this vacuum should be nullified by the air behind it. So this cold air comes in contact with the land, thus causing southwest monsoon and rainfall happens. So this is an example of heat transfer where cold air and hot air transfers between place to place due to the expansion. So next one is radiation. We know between earth and sun there is nothing other than empty vacuum space time. So all these things cannot conduct or convert heat energy. So how? Sun is transferring heat energy into the earth by means of radiation. So when heat radiation, that is thermal radiation or infrared radiation. Infrared radiation is a form of thermal radiation because it exists in the thermal radiation range. So when molecules are vibrating, it emits infrared radiation. So sun emits from gamma to radio wave region. In this, infrared radiation is also coming, which is the major reason for a increase in atmospheric temperature because the carbon dioxide, carbon monoxide, methane, all this molecule absorbs infrared radiation, causing it to vibrate highly. This vibration, what we call average kinetic energy. So this average kinetic energy is nothing but the temperature. So there's absorption of heat by heat radiation by carbon dioxide, carbon monoxide, and methane causes increase in atmospheric temperature. This is called global radiation. Sorry, global warming. So this global warming is due to the absorption of infrared radiation by the carbon dioxide, carbon monoxide, and methane. Majority of these gases absorb these radiations. Other radiation molecules also absorb this radiation, but they are in minor quantities only. So this is how heat transfer occurs. So next we are going to see laws of thermodynamics. So heat transfer is governed by three, especially four laws of thermodynamics. So among them, first law is actually it's not first law; it's actually zeroth law, but it is not the first one proposed. Zeroth law states that let's say a system A, B, C. So in this let's say uh, system A is in thermal equilibrium with B and B is in equilibrium with C. So finally what we can conclude, A is also in thermal equilibrium with C because A is already in thermal equilibrium with B and B is in thermal equilibrium with C. So it is also in thermal equilibrium with the third system C. So this is what zeroth law is mentioning. Like a friend of friend of friend is as well a friend of us. So that is like that only. Zeroth law is stating that if two systems are in thermal equilibrium with the each other, and if any one of the system is in thermal equilibrium with the other system, then the other system is also in thermal equilibrium with the third system. So if two to say clearly, we can state that if two systems are in equilibrium with the third system, then all three systems are in equilibrium with each other. So finally, we can write it like a triangular mode. So this would be a proper notation for mentioning the thermal equilibrium between three states. So this is okay. So next one, first law. First law states that energy can neither be created and nor be destroyed. So according to Einstein's mass energy equivalence, we know that energy can be interconverted into mass, and mass can be interconverted into energy, but they can never be destroyed or created from nothingness. So that is the law stated by the first law of thermodynamics. So what we can say, let's take a system. This system will have a definite amount of internal energy. That internal energy will change. That internal energy will change only when there is a small amount of heat energy flows between the system and the surrounding. That heat energy is taken as Q. It may be plus or minus. Heat exchanged may be plus or minus. That means if plus Q means heat energy is evolved from the system. If minus Q, sorry, if plus Q means heat energy absorbed by the system. If minus Q means heat energy is evolved by the system. Or work is done on the system or done by the system. If it is plus W, we can say work is done on the system. If it is minus W, work is done by the system. So, internal energy change of the system can be given by the amount of heat energy absorbed or evolved, or amount of work observed, sorry, amount of work done by the system or on the system. So here is an analogy for the uh, understanding of first law of thermodynamics. Let's say you take a pump that we used to fill up the gas or air in the tires. So you take a pump, and when you pump the air from your pump to your tire, you can feel the heat in the increase in temperature of the pump when it is overloading. So how it is happening? If the temperature is increasing, what is happening? Internal energy U goes from initial state to a final state. This is expressed as delta U, internal energy change. It is given by UF minus UI, because internal energy is a state function where we find the internal energy change by measuring the initial and final temperature. So between this temperature, how much temperature is increased, that results in the internal energy change. So this is due to the work done on the system. So what should have happened? Internal energy of the system should be increased. That is why temperature of the system is increased. Since we said internal energy is a function of temperature. When temperature increases, internal energy also increases. So internal energy becomes positive here because work is done on the system. So we have to take the plus W because volume is reduced. So this reduction in the volume will give the change in volume results in the increase in pressure also. So totally they cause the increase in temperature to increase. So this is the reason why the pump gets heat because somehow when air cannot escape through the nozzle to the tire tube, it has to convert its work into temperature. That is how internal energy of the system is changing here in the pump. If the air flows freely, there is no restriction in the flow, then air will not compress and it will not generate any heat because there is no work, there is not much work done there. So, next, second law of thermodynamics. So, second law states that no system is 100% efficient. For the simplest explanation, no system is 100% efficient. Exactly to state it, heat energy cannot be transferred from one system to another without spending some energy into the sink is impossible. That is, you need to spend some energy that is impossible impossible beyond thermal equilibrium. So let's say, for example, mm, consider a refrigerator. What it do? What it actually does is reduces the temperature inside the compartment of the refrigerator by exchanging heat from inside to the outside by spending some energy. Without doing nothing, heat energy will not flow from inside to outside because both refrigerator and the surrounding refrigerator is the system, both system and surrounding are in thermal equilibrium. So this equilibrium will not allow the heat transfer between system or surroundings. So how we can reduce the temperature? Because beyond we second law states that beyond thermal equilibrium, heat energy cannot be transferred between system or surrounding without spending some energy to the sink. Here, what we are doing here, if you leave it turned off, it won't change the temperature. Both inside temperature and outside temperature will be the same. So here, how it is working? Because we are using a compressor. This compressor uses a liquid to transmit heat from inside to outside. How this liquid transfers heat from inside to outside? Why there is a need for compression? Because same thing like what we have done in the first law of thermodynamics, like we are using a pump to fill the air in the tire, where beyond the certain limit it releases heat energy na? So like that we are going to compress the gas into liquid by spending some energy. That energy is nothing but electrical energy used by the pump. So this electrical energy compresses the gas into liquid. When gas into liquid, when a gas turns into liquid, what happens? Its temperature reduces because you can see that uh, during compression, temperature increases. To maintain the isothermal condition, valves conduct heat from, let's say, take a piston and compress the gas inside it. So when we compress it, volume is reducing. So collision between the molecule increases, which eventually increases the temperature. So when this temperature is increased, if the walls are not conducting, temperature will remains the same as increased. Once you release the piston, once you remove the force applied, then the piston will move back and reposition itself. But here we are using only metals which conducts heat easily from inside to the outside. So during compression, what happens? This is like a isothermal compression. Isothermal compression. So by maintaining the temperature, it compresses it into liquid. So heat is exchanged between system to the surroundings. So once the liquid is gas is compressed to liquid state, heat is moving from the gas used in the compression to the surroundings. That happens here. Now this liquid is circulated inside through a thin copper tube. So this copper tube will return back to the surroundings. So what will happen? This liquid flows inside and this liquid absorbs the heat inside the system because this liquid is under very low temperature when compared to the, let's say take it as T1 and the system has T2. T1 is less than T2. Eventually heat flows from the refrigerator to the liquid inside the copper tube, and the liquid expands and reaches the outside compression. So here again that compressor compresses the liquid gas into liquid and reduces the temperature. So for this conversion beyond equilibrium, we are reducing the temperature. We are transferring the heat from one system to the surrounding. So in the isothermal compression, the heat energy is again repeatedly transferred between system and surrounding, that is in from inside refrigerator to outside by spending some energy, that we are using electrical energy to compress the gas into liquid repeatedly. This cycle repeats until our required temperature reaches. So this is how the system of refrigeration works. Here it is not 100% efficient because we are spending some more energy. So another analogy is, when you look at the Maxwell Boltzmann distribution, you can see that when the temperature is increasing, it actually widens the graph. When temperature is increased, this graph widens, and the most probable velocity expands and spreads into different microstates, and the distribution of energy takes place. Distribution of energy between microstates happen when a small amount of heat flows into the system without changing the temperature. So here how it is work. So let's say a molecule is vibrating in x direction, x, y, and z. So when a molecule is vibrating in the x direction, in the x direction, it is back and forth. It is vibrating or oscillating. So if you want to transfer this into y direction, we cannot complete it without spending some energy. To transform it from x direction to y direction also, we need to give some push, otherwise it will not happen. But here the total average kinetic energy still remains the same. Still the kinetic energy is same only, but we spent some energy in transferring between other degrees of freedom. So this small amount of energy is the reason for the increase in number of microstates uh, and the redistribution of the energy. So this term we call it as entropy. Here, as the total kinetic energy remains same, our temperature also remains the same. So, a small amount of heat energy is supplied into the system. By keeping the temperature constant, the system redistributes itself into different microstates so that the total kinetic energy of the system remains the same. This is called entropy, entropy change. So this change in entropy is represented as delta S is equal to Q by T. Q is the small amount of heat energy absorbed or emitted. T is the temperature. So entropy change is nothing but the redistribution of heat energy among different degrees of freedom or between different microstates. So this is how entropy of the system is changing. But here heat energy is absorbed but no other work is done. So We are not getting any useful work. This is just a total wasted energy. Like that only we can consider. So there is no useful work done here. That is what happening here. So we will see entropy in detail in the next class, and then we will move into the third law of thermodynamics, which is completely based on the entropy and statistical data obtaining from the microstates of the system.